So what I want to talk about now is instruments used to actually measure the pressure in a fluid. um, and so let's look at pressure measurements. um, and so there's two devices that I'm going to just kind of go over qualitatively. The first one is a manometer. So what a manometer is it's a tube which has this U shape to it and a long column on the other side, where this end is open to the atmosphere. So if we were to put a liquid in here, which would have, if we poured a liquid in, which would then have some height to it, so that height should be the same on both sides. So it has the same height, let's say, from the top. Well, it's at the same level, which means that the pressure is the same at that height, right there. Okay, so now what we want to do is connect this to our sample that we're trying to measure. So this box right here is filled with a fluid, let's call it a gas, which has some pressure. So there's a pressure of the gas inside here. If we hook it up to the manometer, then what's going to happen is this fluid inside here is going to feel the pressure pushing on it. So there's going to be some pressure from the gas pushing on it right here, which is then going to push the fluid to a new height up here. So now there's an imbalance. It's no longer, the levels on the left-hand side and the right-hand side of the fluid and the manometer are not the same. So basically what we've done is we have shifted the level to of a height h, right there. Okay, so we can now use that. We'll use our equation to figure out what the pressure of the gas is. So if I look at this right here, if I look at this side, then the pressure in the gas is equal to basically this pressure over here at some depth P. So that's the pressure. That pressure of the gas is the same right there. And so that's going to be the atmospheric pressure pushing down plus the density of the fluid times G times the height H that the fluid was displaced by. So basically we're using the same equation to figure out exactly what the pressure at the depth is, and now the pressure at the depth is the pressure of the gas, which is hooked up to the left-hand side of the manometer, which pushes the fluid a height a distance h in the open column. And so since this is 1 atmosphere with the manometer, the pressure that we're measuring is 1 atmosphere plus the density of the fluid times G times the height of the column that it's moved. So you can do this with different fluids. You can do it with oils, you can do it with alcohol, you can do it with water, you can do it with mercury. And really the choice of the fluid will then impact basically the height at which this thing is going to. A denser fluid is not going to be pushed as far, so it won't go as high, which is good if you want a compact device, if you want a compact manometer. Or if you have a lot of real estate and you can create a large column, then you can use a less dense fluid like water or alcohol and such. Now, this brings up another really good point, which has a relationship to New England Patriots football, and that is this manometer uses the atmospheric pressure, which is sometimes called the gauge pressure. The fact that when you're measuring something, you know, in normal atmospheric conditions, then you have to take into account the pressure of the atmosphere pushing down um, on the object that you're actually measuring. So if we were to make this measurement in outer space where there is no atmospheric pressure, then you're kind of left with just the displacement um, of the fluid. However, since we are measuring this in our normal atmosphere, therefore you have to take into account that the measurement that you're making is based on the fact that there is an atmosphere. So when there was a big controversy over deflated footballs in the playoffs, um, then I believe between the Patriots and the Jaguars, then there was some discussion about, did they take into account atmospheric pressure? Did they take into account the gauge pressure? So if they had just simply looked at these equations, they would have realized that, they would have to have taken into account the gauge pressure because they were making the measurement in a condition of normal atmospheric pressure. But that's just an aside. The important part is that it's a really simple device that one could construct where all you're doing is displacing a liquid based on the pressure of the thing that you are trying to measure. The second device that you could use to measure pressure is a barometer. So in this case, what you do is we have an open dish of a fluid, and we have a column here inserted into the dish. And what happens is when there is a pressure pushing down on the open dish, let's say the atmospheric pressure, then that is going to force the fluid up into this column right here. And what we leave in here is it's not an open container, but this is a vacuum. So we suck out all the air from the column, and what we're left with is inside is a vacuum. So there is no pressure inside that column. This is a closed system. And since it's closed, then that gap, the little space in there, has nothing in it. It's a vacuum. So in this case, if the fluid is displaced by the pressure by a certain height, h, right here, then we can calculate basically the atmospheric pressure. So the pressure at the bottom here, the pressure at this depth right here, if we use our equation, is the pressure of the atmosphere is equal to the pressure of the vacuum plus the density of the fluid times G times H. Now, with a vacuum, there's nothing inside of it. It's empty space. There are no atoms. There's nothing moving around to bump into each other, to apply forces, to have any kind of conservation of momentum. It's just an emptiness in there. So since there's no material inside the vacuum area, there is no pressure. So the pressure of the vacuum is 0. So in that case, with a barometer, since it's a closed system, the atmospheric pressure that you're going to measure is just the density of the fluid times G times the height. So if you build this kind of a system, then you can basically reverse the process, and you can measure the atmospheric pressure based on whatever fluid that you put inside this dish. Now, we could actually use this now to kind of design or engineer a barometer. So let's say we're trying to measure the atmospheric pressure. So we said the atmospheric pressure is 1 atmosphere, or 1.01 times 10 to the 5th Pascal. And let's say that we use water. So for H2O, the density is 1,000 kilograms per meter cubed. So if we put those into our equation, we have 1.01 times 10 to the 5th is equal to 1,000 times 9.81 times the height h. So to find the height h, we divide by 1,000, and we divide by 9.81. And so when we put that all together into our calculator, we basically get approximately 10 to the 3 meters. Oh, I'm sorry, not 10 to the 3. You get 10.3 meters. You get about 10.3 meters, which since 1 meter is approximately 1 yard, which is equal to 3 feet, then we're talking about a height which is approximately 30 feet. So you'd have to build a column, and people did this during the Renaissance period, back in the the 16th, 17th centuries. You basically build this tube, this column of water, which is in one end stuck in a bucket, and in the other end has 30 feet of water, which can go up and down the column. And so basically you had to strap it to a 3-story building, since a story is about 10 feet. So it would have to be this large column, which would sit in this square in the center of town, strapped to some building that was tall enough to hold it, and then somebody would have to go out there and measure the height of the water column to figure out what the atmospheric pressure was that day. So, if you wanted something a little more compact that you could then, say put in your car and take with you, instead of a 30-foot long pipe with enough water, then let's look at another liquid like mercury. So with mercury, the density of mercury is 13,600 kilograms per meter cubed. So the density of mercury is 13,600 kilograms per meter cubed. So now we can calculate the height, which we said was the atmospheric pressure divided by the density times g. So that was 1.01 times 10 to the 5th pascals divided by 13,600 kilograms per meter cubed times 9.81 meters per second squared. And when you put all of that together, you get a height of 0.760 meters, or 760 millimeters, which is much more compact. That's a much easier barometer to carry around with you, and which is another reason why sometimes the pressures, instead of giving it in 1 atmosphere or 1.01 times 10 to the 5th pascals, it sometimes is quoted as 760 millimeters of mercury.